All right, so to review, we've covered everything we can about spin 1/2. Spin, silver in a magnetic field. All the ground rules for what that is and how it works and all the Dirac notation that you need has now been done. So now we're going to start looking at quantum phenomenon using it. And specifically, we're going to do the uncertainty principle today and all the consequences of the uncertainty principle. And then after that, we're getting into time-dependent quantum. All right, so other than having defined spin operators, that's just SX, whatever, having defined them, be careful. I know on this last homework I also gave projection operators. Don't confuse them, right? This operator, this is not the SX plus projection operator in your homework. That's why I gave it a different label. This just says, what is the X component of spin for a beam of silver atoms coming through an X-oriented magnetic field? That's what this tells you. Okay, then I have one for Y and Z is pretty trivial. We covered last time how, I did one example, but you could literally just do them all and show that you have this relationship with the commutator. Of course, the commutator is, is this. You may be looking at that and saying, oh, hats for everyone. You may be looking at that and say, why would anyone care? Why would anyone care about this? Well, because it's related to the uncertainty principle. Again, some of your backgrounds may have recalled that. Maybe you saw it as an undergrad and you recall it. Maybe you haven't seen it, in which case you're seeing it now. Okay, so what we're going to see is the fact that this is not zero means you have an uncertainty relationship between SX, SY, and SZ. Okay, fine, but what does that mean? All right, let me point this out. Let's do this. Let's ask ourselves, I prepared a beam of silver atoms plus Z with the Stern-Gerlach device. Now I'm asking you, what is the X projection? Now, if you look at this, it's hopefully not hard to figure out that it's H bar over 2. It's plus H bar over 2. Is that right? So I polarized spin in the Z direction, and now I'm asking you, what is the X projection? Is it H bar over 2? What is it? Look at this. I mean, is that it? Yes or no time? No, it says plus H bar over 2. So you got to start talking. You got less. One vote for yes. Any no's? Any no's or just confusion? Look, there isn't much to this. I don't know why, really should be able to instantly say yes or no. Because there's not much here. It's either yes or no. Got a no in the back? Why? Okay, why no?
Because one is SX plus and the other one is SX minus.
It fails the eigenvalue equation. The answer is no. Yes, it does not. That's not the eigenvalue equation. That means that this is mathematical junk. It unfortunately implies, which may or may not be true, which is what we're covering, that you cannot know the SX component, which sucks. So we have to explore, is that really true? If it is true, what can you know? And what are the implications? All right, so let me give an example. Sorry, let me see where I'm at in my notes. Okay, so the answer is no. So let me point out that hopefully you've seen this before, and if not, again, I'm showing it to you. Take that like that NMR thing I showed you. All right, so let's orient something in the Z direction. This is actually a naive view of how spin works. Now that you know something about this, the correct representation of spin is like this. I think some of you have seen this before. So this is, I'll call it SC, right? So this is how you see spin the angular momentum and spin is a type of angular momentum that we don't know what it is. This is actually how you see it represented in three-dimensional space. Some of you might recall seeing this before. It's even in my silly textbook. Right now, so what's happening is the projection onto Z is known because I prepared it, I prepared it in that state, and that's what that means, and you figure that out in your homework. When I'm asking this, it means that I have ran some silver atoms through an SC polarizer and an SG apparatus. So the projection onto SZ is known. So the reason you draw this in three dimensions as a cone is because you don't know where it is in the X or Y plane. Because this is junk. This is junk. You don't know. So you have to represent it this way because now the projection of this vector, because it can rotate about this, like Z is a pole that it rotates around. You can see that its projection into X or Y could be anything. So you don't know what it is. Now, that's awful. And so this is one of those cases where if you truly prepared a pure state in the Z, in this case the Z direction, it has to be specific to my example, then you actually are not allowed to know what X and Y are. And that's it. I mean, that's how it is. And you have to deal with this accordingly. But now the last bit, let me point out to you, do you remember how a 2D NMR works? Right? Remember how you have a proton pointed up due to its magnetic field. A radio frequency burst is able to tilt the polarization to the side, and then it starts rotating. Remember when I said that was because of the uncertainty principle? That's this. But let me point out that the uncertainty principle, and again, I'm actually covering it still. I'm not trying to go into the future too fast. The uncertainty principle does things. Because this actually happens, because this is how nature tricks you into not knowing what the X and Y polarization is, we're able to use that dynamic to force the protons to spin in the XY plane, which is picked up by a copper coil that is the NMR spectrum, that gives you the signal for your transform to the NMR spectrum. So uncertainty principles do things that are useful. So you may not know what X and Y are, and that sucks if you need to know them, but it also does allow you to build further transformed NMRs. Okay, all right, with that said, kind of review, this is kind of foreshadowing where we're going. Okay, so, if a commutator for two operators is 0, therefore they're compatible. Using the language of the book, which I actually do not see in mainstream literature. So just know that. The book says the operators are compatible, or like in the SYZ, that's incompatible because this is not 0. I don't see people use that language in the literature, but that's what the book says. It doesn't matter, it's not a big deal. Okay, so let me prove what that means. Okay, now you have to assume no degeneracy. Degeneracies cause a lot of problems. PX, PY, PZ, those are degenerate. Degeneracies can cause a lot of problems. We have tools to fix them, but we'll start analyzing everything assuming that states are non-degenerate. That'd be like particle in a box. Not a hydrogen atom. Hydrogen atom, once you get past n equals 1, has lots of degeneracies. Anyway, assuming no degeneracy. So let's do our usual dashes, double dash, single dash. I'm taking this straight from the book. Okay, what does this mean? Insert the definition of the commutator. Notice that there is an order to it. Then the VA, ABVA as I wrote it. If you get that reversed, that could be a big problem. Because if you were to write VA minus AB, that would be minus this. So just be careful with that. if you decide to change the definition of a commutator, actually everything would be fine, just never, don't flip-flop, right? So, but anyway, this is the correct definition. It actually kind of matters, we'll see in a little bit. Okay, so now, the way things associate, is this associative? Is this the associative or is this the commutative? I never remember. Right, so I'm just factoring, basically boiling. There we go. All right, child's play up to this point. Okay, now, let's see. Now at this point, I have to admit, I didn't get a chance to look in the book because the rest of the lecture is difficult even by my standards, and I didn't get a chance to look this up. If you assume A and B are Hermitian, and you will see non-Hermitian operators. We haven't done any yet, but remember, Hermitian operators are the ones you never care about. The spins, those have to be Hermitian because those are things you can measure. I mean, Stern-Gerlach literally did all this. Those operators, those which represent their equipment, those have to be Hermitian operators because they were able to measure things that came out, and that's real. So that means that the eigenvalues are real. Okay, now if you assume these are Hermitian, the reason I'm doing that is I'm going to have A act on this one. Now that's important because normally I need the transpose to act on the bra. Remember, transposes, we haven't really covered them. I've told you what they are, but at the same time I really haven't, and that's because they're actually really hard to understand. But if a Hermitian operator A is equal to its transpose, I can just go ahead and have it operate on the bra. Normally an operator can't operate on a bra, that's junk. But if it's Hermitian, then it can because it's equal to its own transpose. Remember, transpose operators operate on bras. Okay, but now if it's Hermitian, I can go ahead and do this. Now there is one thing still though, it's still the other way, right? It's still the other way, so that will be the complex conjugate. And your homework, you have to do some proofs that will help keep all this stuff straight. It is a little frustrating, but anyway. Now here, there's not a problem. A is to the right of the ket. Now this one, there's never any confusion. Now I've acted on A. That's why I'm not writing A again. A has done its job. So I'm left with B. Okay, you may notice now that I can now factor things. I gotta remind myself what the heck this means. Okay. And again, okay, this is kind of dumb. I'm assuming that these are right. I'm saying if they're zero. Right now, like, oh, how did I know it was zero? I'm saying if it's equal to zero. Right? I didn't prove it's equal to zero. I'm saying if it's equal to zero. If the commutator is equal to zero. That is not this case. Okay. Now, if this is equal to zero, now I said before that I'm not necessarily saying what the relationship is between these states. They could be the same state, right? They could or could not. Okay, so if it could be either, you have to make sure that this will hold for all circumstances. Now, if A and A prime and A double prime happen to be the same, if these are the same state, then this is zero, and then everything is fine. But they also may not be. Maybe this is the excited state and that's the ground state, and this is the Hamiltonian. I mean, I can just make up anything, and it better work. I'm giving myself a situation that's actually pretty difficult. That's a Hamiltonian, and that's the excited state, that's a ground state. This ain't zero. Not zero. And as soon as I've derived a situation where that doesn't have to be zero, then that must always be zero. This one always must be 0, or there's a major problem. Again, just one fanciful example is enough to do it. Okay, now what that means is, that means B, sorry, I'm kind of doing this the wrong way, is eigenfunctions of B. Okay, so the A states are the eigenfunctions of the B operator. Okay, so, and what that means is, and look out for this terminology, I hear this all the time, let's write this in matrix form. It's diagonal. Now I mentioned before I don't hear the word compatibility used in the literature, but I hear diagonal all the time. This operator is diagonal. What the hell does that mean? It means that the eigenfunctions are that whatever you're talking about, whatever operator, whatever functions, that they're eigenfunctions of each other. And that means that I'm just writing the eigenvalue equation down. Now I'm going to write something that's going to surprise you. Notice I didn't write A prime as the eigenvalue. Why not? Why, hold on, all of a sudden I've got a new letter there. Why not A prime? Is it always A prime? The number A prime times the state, the A prime state. Why am I doing that? Any idea?
You're operating it on B.
Yeah, it's a different operator. if the B operator gave the same eigenvalue, B is actually A. I guess it could be, right? I keep saying that you have to be careful about what's what. You know, I didn't necessarily say that B is different than A, but if it is different than an A, then it can't be given the same eigenvalue. So it does. So it actually has to be different. Okay. Or what am I talking about, right? That doesn't make sense if the A and B are the same thing. That I'm really being an idiot. Okay, and that means that in the representation of the A basis, that the B matrix would be diagonal. Okay, is Sx in the Z basis, is that diagonal? Is this diagonal? Right. Plus minus, minus plus, plus minus. Those are off diagonal elements. That, of course, is the same for Sy. So now you see Sx and Sy are, if you put on them Sz states, you got a problem because they're not eigenstates. And polarity ensues, right? So there you go. Okay, so there you go. All right, examples where you run into this. So let's do L squared and Sz. Why don't we do that? Now what I'm talking about here, let's go back to our helium atom. Let's do 1s, 2s, and 2p, x, y, z, right? Now, I could write a configuration. Now, helium, ground state, would have 2 electrons in the 1s, and God knows that got beaten into you pretty hard on the two hours ago. But, you know, maybe some electrical discharge, maybe unbelievably high heat. I could put a helium atom, I could put it in an excited state. There's actually all kinds of tricks to do this kind of stuff. So I could put helium into this excited state. This is an excited state. There's nothing wrong with this. Okay, notice what I've done. I've specified L squared L, whatever. I say L squared because when you do angular momentum, remember this is the angular momentum operator. So L times L plus 1. So we often just call that the L squared operator. And I'm talking about P versus S. L squared, L of 0 is S, L of 1, so whatever L times L plus 1 is, that's P. So in this representation, I'm saying I know the difference between S and P. Okay, Sz. Now, this would be for the electron. If I'm talking about S, I'm talking about an electron. You have to be careful about that. Maybe I was talking about something else, but I'm telling you, this is for orbital angular momentum, and this is the electron spin. Notice I use up and up. So I know that. I know that. Because how could I draw it otherwise? So here's an example. These two operators, that's A and that's B. And the wave functions that I write, which, we don't really know what they are. Okay, we talked about that, but we'll assume hydrogenic wave functions. Alpha up, beta down, spin wave functions. I can write these wave functions, and I can act on it with L squared, and it's going to say, hey, you got yourself a p state. And then I can say, hey, is it up or down? Well, they're both up. See, I know all that. If there was an uncertainty relationship between them, I would have something here gets blurred. I can say, well, I know it's a p state, but I don't know if it's up or down, or vice versa. So that's where it matters. So this is an example of how you can know two things at once. Okay. Anyway, okay, so let's go into uncertainty relation. And to do this, we need to understand some statistics. So quantum is ultimately a statistical mathematics. It's just an unbelievably painfully difficult form of statistics. And so in statistics, you have to define this. Here is, what is this? I'm just going to define this thing as A minus the expectation value of A. And what this allows me to do is to define the variance. Typically abbreviated VAR. The variance of A is this. The expectation value of this thing squared. All right? So hopefully not too painful. Fortunately, this can be simplified. Now, I know that it's like, well, how are these different, really, right? Well, here, unfortunately, it's just best to work through these with an example. Okay, left and right bracket are here. You know that those are kets and bras, but I'm going to not write A dash or A double dash anymore because that's just a little much. And remember that this is technically a inner product. This is a number, right? An expectation value. So this is still an operator. So how are these different? That's a number. That's still an operator. Now the ket and bra will collapse on it. So it probably is the same thing squared, right? Probably. But let's just be careful and work through it. Okay. So in fact, yeah. In fact, it is. Okay, this is 2. Oh, here, let me write it out. Okay, so the reason that this ends up being easy ends up being this. Sorry. Yeah, see that foil, right? Sorry about that. 2 minus 1. Wait. Sorry, I've already acted on it. I see what I did. I'm floundering like a fish. I told you that the ket bra will collapse. That won't do it. That's just a number. This is a number, so it stays, but then this is the same thing. And then this is this. Okay, so there you go. Now, if you recall your stats, this is the definition of the variance. The average value, the average of the square of an observable minus the square of the average. And any set of data, like temperature over the course of a year, this will be non-zero. Unless every observable is the same number. So if every day it's 75 degrees for an entire year, this would be 0. But of course, the weather never varied, did it? So that makes sense. If the weather is up and down, even the slightest bit, this would be non-zero, and that's why it's statistical. That's why literally the word variance means how much things vary. All right, so there's that. Now the reason I'm doing this again is that this is going to be a very useful thing for understanding understanding the uncertainty principle. It's how we're going to quantify the uncertainty principle. And in fact, here I can go ahead and write it down. Sorry, let me check this here. So, tell you what, let me give you an example real quick. Let's do one example. Let's do delta Sx squared. So this is the variance. And let's do that for the plus z state. So remember that this, I am putting a ket in a bra, so I do have to have this defined. Now, if I was talking about an Sx polarized state, then this would be 0, because I know exactly what I'm talking about. If I polarized the silver to be Sx plus, then there's no uncertainty. I know exactly what's going on in X. But now that's not the issue. Let's do Z, right? Because let's polarize the thing in Z, and we're in the Z basis set. So again, be careful that I'm not going to be using notation quite the same way. I'm going to be putting a generic ket and bra, but when the dirt hits the road, pedal hits the metal, I'm going to have to give you a indication of what state I'm talking about. So, because it'll change the result. Okay, so again, this is the definition of the variance. Now you may recall last time, now for one, you know, I erased it, but you know what Sx is. And we talked about how last time if you square it, it ends up being h bar over 2 times the identity matrix. So this is just, h bar squared over 4. Okay. And this thing is going to end up being, here, you can work through this. I won't do it because I got to kind of go a little too slow. I can tell you that this is what you're going to run into. You're going to run into plus minus, right? It's probably not too hard to imagine that you're going to run into plus minus because it's off diagonal. Actually, recall the Sx operator. There's no diagonal elements, right? Everything, the diagonal elements are 0. Well, I'm asking what the diagonal element is. I'm asking for the 1, 1 position, right? H bar over 2, 0, 1, minus 1. Is it, or is it 1, 1? No, it's 1 minus 1, right? Or is it 1, 1? I forgot. Well, look, it doesn't matter. So I'm asking, you see what element I queried? I queried this one. I queried this one, so this is 0. Okay, so again, notice that in my drawing, I put it before, you can see why I drew it the way I did as a cone. I know what the SZ is, but SX, I only have the magnitude squared. So you may think like, oh, well, you know it's positive. So what do you know? Well, it looks like you know at least that it is positive. You don't know how much, right? No, it's the square. Square negative, you got a positive. You don't have any idea. You don't have any idea where this thing is pointed in X. So just to show you this is all compatible. All right. Anyone look at that? Bothers me though. Is it 1, 1? 1, 1? Yeah, I thought it was 1, 1. I'm kind of confusing the SX state with the SX operator. Those are absolutely not the same. One's an operator, one's a state. It could not be more different. Oh, it needs a hat. Keep forgetting. Hey, let's get rid of this. Okay, so now let's do the uncertainty principle. For two operators, the variance, their variances must be greater than or equal to their commutator. And you're going to be doing some homework questions, I think, on the next homework with this, so I'm a little bit out of line. Okay, now hopefully, I always teach this in my undergrad class. I hope you've seen it, but maybe you haven't. So this just says that the variances can depend on each other for two operators. Now, unless of course the commutator is 0, in which case there's no interdependence, and there would be no interdependence because the states are the same. So if SX and SC did have a 0 commutator, then my uncertainty in X would be 0, and so would my uncertainty in Z. They would both be 0 because the eigenstates are the same. But that turns out not to be the case. This is not 0. So I got a bit of an issue. And again, it turns out that the degree of uncertainty in the measurement, there's a codependence to them. This is what the uncertainty principle is. Okay, and we're going to prove this. All right? So how do you do that? Now I want to point out that this is actually, maybe don't write this down. This is actually really similar to this. You're basically seeing the same thing. But we have operators in quantum mechanics as opposed to vectors on X and Y. Okay. Anyway, so this is kind of the same thing as that. Just want to let you know that it's not that unfamiliar. Okay, now the proof is, now this is going to really not make sense at first. It will later. I'm going to start with this. I'm going to have a state. I'm writing the bra of a state composed of two different kets. Well, I did the bra over here. Here's the kets. Okay, I'm going to take an inner product. The ket is composed of two kets. Same with the bra. Complex conjugate. Lambda is something. I'll define it later. So this is hopefully an exercise in Dirac notation that should be brainless. I'm praying it's brainless at this point. Right? Alpha, alpha. Now what I'm going to have is lambda star lambda, the absolute value. So that has to be, I want to point out that that's positive. That comes from the beta beta inner product. Then I'm going to have a cross term. Here's the weird parts of the foil. And it's not 2 times lambda times alpha beta or beta alpha because the complex conjugate kind of messes that up, right? A plus b squared is a squared plus 2ab plus b squared. You almost see that, except that since you're dealing with complex conjugates, it's not quite right. Anyway, foil, hopefully this is child's play. Okay, now again, let's not go too nuts. So let's assume that the inner product is 1, and then we're assuming that the states are normalized. And here's the thing. This is if alpha is equal to beta. If that's the case, this has to be greater than or equal to 0. Yeah, it has to be greater than or equal to 0. And that would be because you may recall that I did this before, right? When we were starting to learn quantum mechanics. I said the inner product of the state with itself is greater than or equal to 0. Now you recall that? Now what I've done here, of course, I just said that you can do this, and I hope that that's been made clear. There's nothing wrong with making linear combinations of states. That's totally fine. Hell, maybe lambda 0. But anyway, so this is a statement about quantum mechanics I made a long time ago. I've now done this, and I've proven this relationship. Now, here's the damnedest thing. If alpha is not equal to beta, then this actually is still true. And how the hell is that? How does that happen? Well, because let's say that these are orthogonal states and those are 0. 1 plus a number that has to be positive, it's an absolute value squared. Positive, positive, it's still greater than or equal to 0. So under the only two, is or isn't, that covers every possibility. Is, well, we covered why that's greater than 0 at the very beginning. Isn't, well then it's safe to assume the states are orthogonal, then you've got 1 plus a positive number is definitely greater than 0. Okay, now why am I doing this? All right, now the reason is that I can actually define these in terms of a delta operator. I'm foreshadowing. Let me, oh God, sorry about this. I'm gonna have to work to the left. Actually, I've got one more thing to do. One more thing to do. I have to get rid of this lambda. And on your homework, you're going to be doing a lot of explorations of this. Now, at first, this is going to appear that I'm going to define things in a way that give me the result I want. Well, that sounds like cheating. But on your homework, and not this one, but the next one, you're going to be looking at this relationship and why it makes sense. So I'm going to leave it for that. But let's go look at this stuff, and let me define lambda this way. Okay, if I do that, let's look at what alpha and alpha would be. Sorry, let's look at this. I'm going here. I'm here. I'm just writing the same thing. Okay. Now, again, I don't write the stars very correctly. And again, that's equal to 0. All right, now I'm going to insert this definition of lambda. Okay. Yeah. Here, beta, beta. All right. So this is lambda, complex conjugate. The other guy, they both have a 1 over beta, beta. There we go. And we do the same here. Alpha, beta. That's a minus sign, yep. Only one of these. And minus sign, so there. And as a bit of a bit of a handful. Let's do that. Okay, so,
One question.
uh-huh.
Alpha, beta, and beta.
What will I have complex conjugate? Right.
Got it.
Alpha, beta, beta,
Yeah.
alpha, because it's complex conjugate. Right. Okay, you may notice that when I factor this, I mean, these cancel. Yeah, those cancel, so you end up with alpha. Minus, actually, that's typically the absolute value. Beta alpha squared over beta beta. And therefore, now I'm just going to do 2 steps of algebra. Okay, I just did 2 steps of algebra. I brought this term over to the right and I multiplied through by beta beta. So alpha alpha, beta beta. Okay. Now this, again, is bringing me very, very close to the uncertainty principle. Now how does that work? Now here's the part I was kind of babbling about earlier. Oh, sorry about that. So this is why I really need a bigger board. This is one long ass derivation, isn't it? Okay. Now, knowing that I never really defined alpha and beta, and this is kind of cheap, but it'll work. I'm going to say alpha is due to the action of this operator. So I'm going to redefine it. So now the reason this is valid is that a function of an operator is still an operator. So in an operator, opting out a ket is another ket. So, and I never said what alpha was anyway. So I'm going to say alpha is actually now the result of the, whatever delta, delta as defined before. So I can, again, everything's kind of arbitrary in operators and functions of operators turn states to other states. So this is actually 100% valid thing to do. And what that means is that now I've got this. Just writing stuff down. Okay, so you got that. Okay. So the thing here is we're awfully close to the uncertainty principle, but where's the commutator? Right, so it's already looking like the uncertainty principle. Unfortunately, I don't have the commutator there. About to run out of time, so let me give you a feel for how this is going to go, because I just was going way too slow. This is actually one of the more difficult parts. What you're going to do is you're going to take, so this is, we're going to go in a different direction. What you're going to do is this. Now this is going to be, now this part is cheap. Watch this. You're going to love this. See how that works? This minus that plus that. This and that are 0. So 1/2 of AB plus 1/2 of AB is AB. So this is stupid. The reason I did this is that I can now write this. See, here's your commutator. Almost. You have an anti-commutator. Remember I was telling you that you're only going to see an anti-commutator once your entire career? Here it is. The only time I've ever seen an anti-commutator used for anything was in this proof. Okay, so since I'm kind of out of time, let me point out that I need to now turn this into a number, and I do that by, of course, doing an expectation value. And I will now, this is the thing you're doing on the homework next time. You're going to play around with that lambda thing, and you're going to also explore this a bit. And I am hopefully being quite careful with where my graphics are. That really is important. Okay. This is anti-Hermitian. And this is Hermitian. This is why I run out of time very stupidly. It turns out that this thing has to be imaginary. So remember, messing around with operators creates other operators. So this is, here's delta. Okay. Yeah, I did that right. Okay. Delta is a function of the operator. It's A minus its expectation value. So it's basically still A, same as B. This commutator is AB minus DA. So I've just done a lot of manipulation of the operator. But no matter what, the net result is still an operator. Just like SXSZ, like on your homework, is still an operator. I don't know that it has a name, but it's an operator. Now it turns out that this operator is always anti-Hermitian. That means that its eigenvalues are imaginary. Just like the anti-commutator is always Hermitian. So these eigenvalues are real. Now the last step of the proof then is what we're going to do is we're going to get rid of this one. We're going to wipe it out and say that this is always greater than that. And notice it's right here. So that's basically the final step of the proof. So this thing is absolutely always greater than the commutator. So recall that the uncertainty principle has this, it has that, and it's got to be greater than or equal to the commutator. But I don't see a commutator in here. So this is my problem. So what you see we do here is insert the commutator. And I'm going to make this work by simply wiping this out, which will, and then I'm going to put that in anyway. You'll see it next time. I shouldn't talk anymore. I think it's a bit confusing. Anyway, next time we'll finish the proof because I got about another 10 minutes to go. And you're also going to be doing it again on your own.